Hi everyone, this is Bill Stubbs. Welcome to the second video in my series, Dissecting the Standard Model of Particle Physics, this one titled, Rise of the Quarks. In this video, I continue discussing the contents of my book, Three Quarks Missed the Mark, by looking at the initial suggestion that baryons, including protons, might be made of unusual particles called quarks, the ultimate discovery of particles inside the proton, and the campaign launched after the discovery to make those particles quarks. Let's jump right into it. In the early 1960s, faced with a growing list of subatomic particles, physicists searched for some way to make sense of it all. Several physicists, including Murray Gell-Mann, determined that mesons and the spin 1/2 baryons could be arranged in octets he called the eightfold way. This suggested their underlying symmetry group should be SU8, but it was known to be SU3, so in 1963, Gell-Mann attempted to produce the octets in SU3 symmetry. Using a unitary triplet T made of a singlet S with a charge of Z and a doublet UD with U having a charge of Z plus 1 and D a charge of Z, he found he could produce baryon octets using combinations of B, T, and T bar, where B is a neutral baryon singlet, and T bar, the anti-triplet, which has particles with the same masses but opposite charges of the triplet T. The most interesting combination to him was spin 1/2 triplets with Z equal -1, because the three members of the triplet became D-, S-, and U0, which along with the neutral baryon B0 produce charges that parallel the charges of the four known leptons, the electron, the muon, the neutrino, and the antineutrino. However, he also found that if he used spin 1/2 triplets with non-integral charges, he could produce the baryon octet without the neutral baryon component B0. When he set the charge Z equal -1/3, the triplet members became U with a charge of +2/3, D with a charge of -1/3, and S with a charge of -1/3. It was at this point that he claimed to have given the members of the triplet the name quark, which he said he initially thought to spell KWORK. However, he ran across the word quark, QUARK, later in James Joyce's Finnegan's Wake and adopted it as the spelling. With the quarks, he was then able to build baryons from combinations of three quarks, QQQ. For example, the proton would be 2 U quarks and 1 D quark, and the neutron 1 U and 2 D quarks, and mesons from a quark and an antiquark, QQ bar. For example, the negative pion would be a D quark and an anti-U quark. The baryon number B of the quarks was arbitrarily set to 1/3 so that three quarks in the baryon would always give it a baryon number of 1. Antiquarks got a baryon number of -1/3 so that with the quark in the meson having a baryon number of 1/3 and the antiquark a baryon number of -1/3, the baryon number of the meson would always be 0. With fractional charges having never been observed in nature, could quarks be real particles? Gell-Mann seemed to imply he thought not, writing in his February 1964 Physics Letters paper, "It is fun to speculate about the way quarks would behave if they were physical particles of finite mass instead of purely mathematical entities as they would be in the limit of infinite mass." In the mid-1960s, few physicists thought the fractionally charged quarks were real particles. In fact, to openly or formally suggest that they were real particles could be career-limiting at the time. In 1967, particle physicists from MIT and Stanford began collecting data from experiments done in the newly built Stanford Linear Accelerator Center, or SLAC. The experiments, called deep inelastic scattering, fired extremely high-energy electrons up to 30 GeV at stationary proton targets. A decade earlier, Robert Hofstadter had performed similar experiments using a smaller accelerator at Stanford, the High Energy Physics Laboratory, HEPL. For linear accelerators firing electrons at stationary protons, the center of mass energy, E sub cm, is approximately equal to the square root of 2 times the mass of the proton in energy units times the kinetic energy of the electron. HEPL produced electrons with energies up to about 600 MeV, corresponding to center of mass energies of about 1 GeV and electron wavelengths just over 1 Fermi, which becomes the electron's diameter at this energy. The electrons scattered off proton targets elastically, revealing that the proton was not a point particle as was currently thought, but had a diameter of about 1.7 Fermi. At 30 GeV, 50 times the HEPL energy, the center of mass electron energy is about 7.5 GeV, making the SLAC electrons have wavelengths of about 0.17 Fermi, short enough to penetrate the proton rather than bounce off it. The scattering cross-sections can be determined from the electron scattering data comprised of the scattering energies and scattering angles. An expression for the differential scattering cross-section can be formulated from QED, quantum electrodynamics. Using it and the scattering data, information about the structure of the proton can be obtained. The first SLAC runs used electrons with energies from 7 to 20 GeV, making their wavelengths and diameters 0.34 to 0.20 Fermi, about 1/5 to 1/8 the diameter of the proton, respectively. Once the electrons reach energies high enough to penetrate the proton and collisions become inelastic, physicists expected the scattering cross-section to quickly drop off and go to 0 for the higher momentum transfers q squared, indicating the electrons were passing through homogeneous protons. But much to their surprise, the cross-section remained substantial and relatively constant over a wide range of momentum transfers. Reminiscent of the Rutherford gold foil experiments, the data revealed electrons were hitting something hard inside the protons. The proton had internal structure, likely particles. Could these particles be the quarks Gell-Mann had proposed a few years earlier? This Feynman diagram depicts what is thought to happen during the collision. As the electron approaches the proton, it dispatches a virtual photon, causing the electron to lose energy and scatter at some angle theta. The virtual photon interacts with the structure inside the proton, causing the proton to shatter into several fragments. If the particles the electrons are scattering off are quarks, then they must be spin 1/2 charged particles. The MIT-SLAC team devised some clever ways to determine the charge and spin of the particles. Using the scattering data, 2 proton structure functions, W sub 1 and W sub 2, can be extracted from the differential cross-section expression. The W sub 1 structure function provides information about the charge distribution, and the W sub 2, the momentum distribution, inside the proton. The structure functions are functions of q squared, the momentum transfer, and nu, the difference between the initial electron energy E and its scattered energy E prime, or nu equals E minus E prime. James Burkane of SLAC theorized that if protons contain charged particles, then as nu and q squared approach infinity, the structure functions W sub 1 of nu and q squared and W sub 2 of nu and q squared should become functions of a dimensionless variable x. Then, the 2 structure functions W sub 1 of nu and q squared and W sub 2 of nu and q squared could be replaced by 2 structure functions f sub 1 of x and f sub 2 of x, as shown. In 1968, a plot of nu W sub 2 as a function of nu over q squared using data from the SLAC E49 experiment showed that all the data tracked along a single curve regardless of the electron energies. This indicated the structure function is not dependent on the electron energies built into nu and q squared. Consequently, the scattering was exhibiting what came to be known as Burkane scaling, indicating the electrons were scattering off charged particles inside the proton. So the particles inside the proton met one of the criteria for being quarks. Also in 1968, Curtis Callan and David Gross devised a way to determine the spin of the particles inside the proton. Using current algebra, they determined that if the two structure functions f sub 1 of x and f sub 2 of x are related by the equation f sub 2 of x is equal to 2x f sub 1 of x, or 2x f sub 1 of x over f sub 2 of x equals 1, then the particles inside the proton are spin 1/2 particles. In the graph shown of 2x f sub 1 of x over f sub 2 of x versus x using SLAC data, for x greater than approximately 0.25, the values of the ratio are scattered about the value 1, implying the particles inside the proton are spin 1/2 particles. From the SLAC data, it appeared the proton was made of charged spin 1/2 particles. But were they quarks? By 1969, having found evidence of charged spin 1/2 particles inside the proton, the idea of the proton being made of Gell-Mann's quarks became more appealing. That year, Parton and associate Emmanuel Pascos analyzed the initial SLAC structure function data to determine if the proton contained 3 particles as Gell-Mann proposed. If so, it would be hard to argue against the quarks. They used a theory devised by Richard Feynman he called Parton theory, in which, in the infinite momentum reference frame, the electron is considered stationary and the proton moving toward it. This causes the particles inside the proton, the partons, to slow down due to relativistic time dilation. Parton theory then assumes an impulse approximation applies that causes the partons in the proton to momentarily separate from each other. The partons all travel in the direction of the proton's motion and each carries an equal fraction of the proton's momentum. The electron scatters incoherently off a single parton in the proton, and the scatter is elastic, providing momentum information about the particles inside the proton. According to the theory, if there are n particles inside the proton, then each particle should carry a fraction 1 over n of the proton's momentum. Consequently, the f sub 2 structure function values should peak at that momentum fraction and approach 0 as x approaches 0. This meant that if the proton is made of 3 quarks, the proton f sub 2 curve should peak at about x equals 1/3 and look something like the curve shown. Instead, the measured f sub 2 curve looked like this, flat from about x equals 0.08 to x equals 0.2, then gradually declining to near 0 as x approached 1. From this, Parton and Pascos concluded that the proton was not made of just 3 particles. So, it looks like the particles inside the proton are not Gell-Mann's quarks. Nice try. But wait, maybe they are. Based on the shape of the f sub 2 curve, Parton and Pascos assumed that f sub 2 stayed constant as x approached 0 from x equals 0.2, even though they had no data from x equals 0.08 to x equals 0. They determined that the only way for this to happen is if the proton is made of the 3 quarks but also has a distribution of quark-antiquark pairs inside it. The 3 unpaired quarks, now called valence quarks, define the proton and are Gell-Mann's 3 quarks, while the quark-antiquark pairs are virtual particles called C-quarks and basically fillers. From this extrapolation, particle physicists would build the quark empire currently in place. And it appeared Gell-Mann's quarks were really inside the proton after all. But is the proton really made of quarks? In the next video, I will show why the answer to this question appears to be no.